solution for question 10 that I gave you. So we have a pulley system here, a mass 2m off the side, and then if we let this go, that would travel linearly while the pulley would rotate. So we need to look at the force causing that to travel linearly, and we need to look at the moment or the turning effect causing that to rotate clockwise. So let's start with this linearly, and it's a straightforward connected particles question, so we look at the two of them separately. We've got the 2mg downwards. If it's got a weight, it's got a mass. There's a string connected to it, so there's a tension upwards, and it's accelerating downwards. And I'm writing the acceleration as x double dot, the second derivative of the displacement. So we get 2mg minus t is equal to 2ma or 2mx double dot. That's the linear one. Okay, rotationally then. So rotationally, there's a tension downwards. That tension acts a distance from the center point, and that center point is a distance r away from the tension. So the moment is going to be t by r, which I have here. That's going to equal the moment of inertia multiplied by the second derivative of the angle. So the angular acceleration is what that is. So I theta double dot. Because it's rotating about the center point, we take the moment of inertia of a disk about the center point as the disk is spinning, so that the axis is perpendicular to the plane. So that's a half mr squared by theta double dot for the angular acceleration. Cancel an r on either side, and then I'm bracketing the r by theta double dot. And the reason I'm doing that is because we know that r by theta double dot can be replaced with x double dot, the acceleration. So the second formula there, tension, becomes a half mx double dot. So basically we have 2mg minus t is equal to 2ma, and we have the t value is equal to half ma as well. Now let me reveal the rest of it. All that needs to happen after that is that you take the t value, you put it in there, which is what I've done in that step, simplify it, you get the acceleration as 4g over 5 meters per second squared. Sub that acceleration into that equation there, and you get the t value. So if you just put the t value into the chat function while you're watching it, just so I can see what value you have. I'm going to go on to the second question. So same idea. In this case, we have a particle that's rolling down. As it rolls, it's got an angular acceleration. It's also got a linear acceleration. I have a weight downwards as my force vertically downwards because it's got a mass. I have a reaction. That reaction should be starting at the point of contact between the two objects. And I've got a friction parallel to the plane, which is also at the point of contact between the two objects. So it's a connected particles question again, basically, with an additional rotational effect. So I need to make sure that my forces are either parallel or perpendicular to the plane. They're good, but we need to resolve the weight mg. So they're the components of the weight, in which case then I apply F net is equal to ma parallel to the plane. So it's that force minus that is equal to the mass by the acceleration, which is x double dot, and then those two perpendicular to the plane are equal. So job done there. Now let's look at the rotational effect. So remember, it's the moment that's causing it to rotate, and the moments here, if I ignore the components, I'm going to look at mg, r, and f. R and mg act through the center point, so there is no turning effect there whatsoever. So there's no moment caused by those. The only moment is caused by the friction force, which is a distance r from the axis of rotation. That's why I have the moment as F is equal to r. So the moment is equal to I by theta double dot. The rotation is through the center of the disk, and the moment of inertia again is that value, multiplied by the angular acceleration theta double dot. Just like with previous questions, the r's will cancel, or theta double dot then can be replaced with x double dot. So what I end up with is F is equal to a half m times the acceleration. And just like the previous question, I sub that in there. Now that will give me an acceleration of 2g over 5 meters per second squared. The second part of the question is to find the coefficient of friction, with which the object just is on the point of slipping. The only formula that we have that's got the friction force in it is that. So I'm going to put the acceleration in there. I'm going to get the friction force, and then F is equal to mu r is that I can solve for the coefficient of friction. And that's what I do in the final section there. So that's the homework corrected.